All right. Hello? Maybe this does need to be louder. It is time to stop talking. Okay. Is that better? How y'all doing this beautiful Monday morning? Any questions about the project before we move along? How many of you have started? More importantly, how many of you have not started? Come on. Come on. I know somebody hasn't started. Who hasn't started? No one's going to fess up? Pardon? Yeah, probably not. So I can tell from a few people's faces, though. So, okay. Any questions about the project before we go on? Yes? Uh-huh. Yep. Okay, so if you're overloading your operators and you're trying to set the pointer inside the class, you are making a mistake. And the reason for that is if you look at the data file of the subjects that come in, it has the subject ID in the group. There is no next pointer. So the overloaded operator should not be trying to read a pointer value from the file. Send me an email with your code. Let's talk about offline. Yep. You have what final? The very challenging and difficult final that I haven't yet written? That one? Yeah, sorry, that one doesn't exist. But yes, yes, yes. I will send you an email that has a list of all the topics. I will send you some practice problems. The exam will be. Can we do that later? The exam will be. I'm gonna try and do it for Gradescope again. Did you all like Gradescope this time? Yes. How many of you liked it? How many of you didn't like it? Okay. So the exam will be a little bit more Gradescope friendly, which means instead of having like a page where you have to write 100 different little things, there will be fewer answers because that is more amenable. Just to give an idea. And yeah, I'm going to send out the thing ahead of time. I always do that. I don't know. I don't know. I never check until like the day before. So, and if I have the exam time wrong on the syllabus, which happens about 50% of the time, you need to let me know. Anybody looked at the syllabus and realized, is the exam time I have on there right? Okay, so, because for some reason, I've never actually figured out how I managed to screw it up, but I screw it up about half the time. It's a mystery to me. Yes, sir. How exactly to grade for style and structure? Same thing. We'll look at your code and just run through. And so the auto grader doesn't check the way you do input, which is pretty simple in this one, right? Because you're just giving it 2 file names. So we'll do that by hand. And then I guess I could write the auto grader to do that, but I didn't. And then for style, we'll read your code and try and give you constructive feedback. So I'm a little behind on the grading for project 3 and 4. And shortly I'll be behind on project 5 too. But the good news is that once these classes are over, I don't have to teach classes anymore, and I'll have more time for grading and stuff. So it'll all get done by the time that you have to have your grades in. So. Any other questions? And I'll talk about the final exam more next time. So. Going once, going twice. Let me ask you all a question. How many of y'all are going to take more computer science classes again someday? How many of you are never going to take a computer science class again if you can avoid it? It's okay. Seriously, I won't have my feelings hurt. If you're a chemistry major, I took 1 chemistry course, and that was too many for me. So all right, well, good. Okay, so let's pick up where we were last time. Last time, do you remember what we were doing? We were talking about destructors. Destructors. What happens? What are destructors? Can delete things, yes. Yep, destructor is a method that's part of a class that is there to clean up when the class is finished, right? And the destructor that we were looking at before was this one, right? Tilde node. How do we know this is a destructor? Because it has the tilde in front of it. And if we looked at our destructor right here, what is our destructor doing? It's just printing something out, okay? It is just printing something out. Here's my question for you. Is it normal or common or expected for your destructors to print things out? One more time. No, it is not. Why do I do it here? For educational purposes only, okay? So when you're writing your code, you do not have to have your destructor print out. You may want to for scaffolding just so you can see what's happening, but you don't have to do it just because I'm doing it here, okay? And all we had was we had the node printing something out when it finished, and then here's what we did. We declared a node 1, we declared a node 2, we made it so that we could specify a value. We created the node 17 that was nameless, and then we deleted nameless. Let's take this delete out again just to remind ourselves of where we were. And so we compile this thing called node 5. And when we run, we can see that the static things get created, right? And then the nameless thing gets created. And then the static things are destroyed. What happened to the nameless thing? It did not get destroyed, okay? It did not get destroyed. And if we go back to look at the code, we can see what happens, right? Because this node 1 and 2 were statically allocated, which means we define them there with a name, they only exist inside these curly brackets, right? So when we reach the end of main and these two things go out of scope, the destructor gets called automatically. What happens here, though, is this thing gets called, when we reach the end of the curly brackets, this pointer to the node goes out of scope, but the node itself does not. It does not because it was created using new. So the only way we can reach that node to get it destroyed is to use delete. Everybody with me on that? Is this ringing any bells? Are you all just willing to trust me on this? Yep. Okay, we haven't actually talked about when you need a destructor. We're going to get to that today, okay? Right now I'm just trying to show you how they work, and soon we will talk about why you need them, and then we'll talk about how to build one for the case that we need. So, yep. Okay, what is this thing right here? Of, also known as a pointer to a node. So just like any other variable, when this goes out of scope, that variable, only exists between these two curly brackets, right? Like every other variable, it only exists. So we have a variable, it happens to be holding the address of something. And when it goes out of scope, it will go away. It just won't exist anymore in the same way that node 1 and node 2 don't exist outside those curly brackets. So that's what I mean when it goes out of scope. So we'll have a pointer to something. The pointer will go out of scope, but the thing it is pointing at will still remain. Okay, everybody good with that? Remember our pizza analogy? Who was the guy who knew where to deliver the pizza? Dan or Dale or Dean. Yeah, Dean knew where to deliver it. This is like if you tear down Dean's house, and hopefully he has a chance to escape. If you tear down Dean's house, that doesn't mean the place where you're delivering the pizza doesn't exist anymore, right? Because the place that holds the address is different than the place that holds the value. All right. Everybody sort of see what's happening here? Questions about this before we go on? This is just a refresher from last time. Yeah? When you lose the pointer to this, that node is lost. Now, secretly, I'm going to tell you something. That is, when your program terminates, like when your program finishes running, the operating system will clean up your mess behind you. Okay? So the operating system will hunt down that node and kill it. Okay? It will. That being said, a lot of times there are programs when you're writing them that don't actually finish. Like there are programs that will run indefinitely long period of time, like the operating system on your computer, right? Like, so you actually do have to worry about destroying these things because otherwise you will get memory leaks. Did I tell you about Windows 95 memory leak? Right? Because this is literally what happened. They had a pointer that was keeping track of a program, they deleted the pointer to it, and they just left stuff there, and eventually the memory filled up and crashed. That can happen to your program, okay? So we have to try and delete things. Other questions? Okay, so we can see things getting deleted, and right now all we're doing is printing them out. So let me show you actually one more thing, just so I can convince you of this block scope. Do you remember that we said that if you put things inside curly brackets, even inside a function, that was its own scope? Thank you. So let's create a node 3 right here, and here's what we're going to see. We'll see it get created, and because it's in this inside those curly brackets, when it reaches the end, it should be destroyed as well. Okay? So okay, so here we go. We see using value constructor to make a node, a 3 node, goodbye from the node with 3. So what happened is because we put it in curly brackets, this variable 3, named 3 right here, only existed inside those curly brackets, right? And so we can see the effect of that is we make the node, and then when it reaches the end of its scope inside the curly brackets, it goes away, and we see the destructor fire, and we see it getting destroyed. Everybody good with that? Okay. So everybody understands, right, that when things go out of scope, they go away. When they go away, the destructor gets called. Check? Everybody understands that if you've created something with new, the only thing that's getting automatically destroyed is the pointer to that thing, but not the thing itself. Check? All right, who's with me? Yes? You're always against me. Okay, yeah. So what we're saying is that when an object goes out of scope, when it gets created, it calls its constructor. When it goes out of scope, like outside of the curly brackets that surround it, it gets destroyed, right? But for a pointer, only the pointer gets destroyed, not the thing that was created with new, right? And we saw that because when we didn't explicitly use this delete command to delete it, it would hang around. Everybody with me on that? Okay. So let's look at another example of this. So here is just the same node class as we've been talking about. This one does have the modification so that we can create a new node with a value. It has that extra constructor. It still has the destructor that prints things out. Now let's take a look at the linked list class. Okay? All right. Does the linked list class currently have a destructor? How many of you say yes? How many of you say no? The yes people, where's the destructor? All right, there is a default constructor that gets created, but we haven't defined one. So both of you are technically correct. That was my trick question of, I don't know, that particular 15 seconds, okay? So I like trick questions. Let's say we wanted to add a specific destructor to the linked list. What would that look like? Squiggly? Squiggly linked list, like that? Mm-hmm. That is correct. And then I'm just going to do a little cutting and pasting here because it'll be a little bit faster. And so here is our linked list destructor. And for now, all we're going to have this do is print out. Okay? Are you good with that? Is this something that we normally do in constructors and destructors? Why are we doing it here? Yes, for educational testing purposes only. There's no reason not to, but there's not really any reason to. Okay, so now we've added the destructor. That was pretty easy. Let's actually go and see how it works, okay? So here we are in main. Let's just create a linked list. And that's it. Now let's compile this and see if it works. This is node 6. Linked list being destroyed. Yay, that's nice, isn't it? So we've successfully added our destructor, and everything is sort of fine. Okay, if you really want to get precise, yes. Did I mention last class that towards the end of the semester I get sloppy? So, okay. Does that make you happier? Just like the The compiler will create a destructor for you automatically. It will also throw a return 0 in for you sometime, so, if you're good. And depending on the compiler. Actually, that matters more than if you're good or not. Okay, so here we are. And just for fun, let's put this inside some brackets, okay? So it exists in its own space. Okay, everybody realize what's happening here? Right? Linked list only exists between these curly brackets. And if we compile it again and run it again, we see the same thing. The linked list is being destroyed, but it's really being destroyed for this. And you know what? We're going to do one more thing. So now what we're going to do is we're going to be able to run this. We'll be able to see what happens inside these curly brackets, and then we're just going to hit enter to continue. So we'll know that the program is still running. Okay? Is the program still running? What's it doing right now? Okay. Does that make sense? See what I just did there? So what I want to do is I want to see what's happening in this particular scope between these curly brackets, and I don't want the program to end before we have a chance to tell it to end. All right? Who's with me so far? Good. All right, awesome. All right, so we have a linked list. What do we do with linked lists? What can we do with this? Let's add an element here. What number would you like to have in this element? Good choice. Only one element? Do you want some more elements? Okay, so now we're going to be able to see this linked list. We'll be able to see what happens when we add these elements, and we'll see what gets destroyed. Okay? Everybody excited for this? So we're creating a linked list. We're adding 3 elements. Then, because it goes out of scope, the linked list is getting destroyed, and then we will have to hit enter to continue. So, okay, so we used the constructor to make a node, another node, and another node. Then the linked list was destroyed. Where are those nodes? They're where? In the list, but the linked list was actually destroyed. It's not there anymore. Yeah. Yes, it is in the memory somewhere, right? Because we created new things and we put them in memory. How can we ever get to those things now that the linked list is gone? What was that? We can't. They are lost. So what ended up happening is we created the linked list class, right? We created an object of that class. Inside, there was a pointer to the linked list that had these nodes, and we created those nodes. And then the linked list got destroyed. What happened to the nodes? They're there. Where is there? In memory. How do we get them back? Yes. If we ever delete the linked list, it will be safe. But if we delete the linked list, how can we get the nodes back? How do we get them back? We cannot. Is that good or bad? Bad, right? Because if you have a program that is, a little space here. If you have a program, and our programs aren't doing this, but later on you might be creating many different linked lists and destroying them, you cannot have these nodes be left over, or you will fill up your memory, and then you will be sad, and your program will crash, and your computer will grow exceptionally slow. Okay? Bad things will happen. So what do you think we need to do in the linked list then? In the linked list class? We need to do what? Okay, so when the linked list class goes out of scope, what happens? What happens to the linked list object when it goes out of scope? The destructor gets called, right? The destructor gets called. At that point, before it goes away, we have an opportunity. And we have the opportunity to get rid of these nodes we have created before that pointer to all those nodes is lost forever. Understand? So we have a pointer in the linked list class. That's the only way we can reach those nodes. If we let the linked list class go away without reclaiming all those nodes and destroying them, they will be there forever. So the destructor of the linked list class is the place where we have an opportunity to clean up that mess and clean up all those nodes. Does that make sense to everybody? So you're going to see this as you go forward in computer science over and over again, because you're going to create different things that that you will eventually have to clean up. So for classes that use new to create things, you will almost always have to have a corresponding delete somewhere in the destructor for that object. Okay? Everybody with me on that? Because we have to clean up our mess. Yes, sir. Okay, so the question is, the destructor for the linked list. The destructor for the linked list, does it just delete the default destructor we have? That's all it does, is it deletes just the first pointer off into the linked list. It does not delete any of the other nodes. So if the compiler won't do it for us, who has to do it? We have to do it, okay? So what we're going to have to do is we're going to have to figure out how we delete things and delete everything off the list. Okay? Everybody understand the motivation behind this? Okay. 1 minute break in place. Stand up and stretch. When we come back, we will talk about how to delete things from a list. That's important. All right, welcome back. Welcome back. Welcome back. Okay, so like we did last time, before we start coding, what are we going to do? Algorithm, yes. Before you start coding, what do? You come up with your algorithm before you start coding, okay? So let's draw some pictures to think about our algorithm before we start coding. Does that sound like a good idea? All right, so let's do what we did last time and see what's going on. So here's our situation. We have some linked list. And this one, the particular values are different than the example we were using, but we have some linked list. And we have a head pointer, and it points to a node, it points to a node, it points to a null that's null, and we want to delete everything on the list, okay? So that is our start state. That is our beginning state. What does our end state look like? What's this going to look like when we are done? Nope, not blank. Yes? The nodes will be gone, but head will still be there. What is head going to look like? Null. So this is our beginning state, and our end state, our desired state, is this. We want head to be null, but we also want all these nodes to be gone. We want them to be destroyed. There is a difference between just setting head to null and destroying everything before setting head to null, right? Everybody see the difference? We want them to actually be destroyed. So the question is, how do we get from this first state to this last state? Anyone want to raise a guess, venture a guess, what we're going to need? You do have to delete things by using the pointer to them, yes. Can we just delete head right away? Why can't we just delete head right away? Because if we just delete the first one, the others will remain, right? So we have to find a way to go all the way through the list and delete each one in turn. So what are we probably going to need? What did you say? A temp pointer? You mean our good friend temp? That's exactly what we're going to need. Okay. So we have the head of the list, we have temp. What do we need to do next? What do you mean traverse through the list? Okay, so we have to move a pointer and delete everything one by one. Which pointer do you want to move? Okay, in this case, you can move temp if you want to. Personally, and this is the only situation where I would do that, I'm going to move head. And the reason is because we're going to make sure head is always pointing at the head of the list, and then we will delete things. Okay? So what will happen, and there's tons of ways to do this, we'll probably look at another one. What we're going to do is this. We are going to not lose our head pointer. We will advance head to point at the next node. How do we advance head again? How do we change head to point at the second node? Head equals head arrow get next node. Yeah. Okay, so we advance the head pointer. Now what do? We call delete on temp. And that node is gone. It is deleted. Okay? It's gone. Everybody with me so far? Mm-hmm. You literally say delete temp, delete parentheses temp. Exactly. New gives you a pointer to a new node, and the node actually exists. Delete follows a pointer to a new node, to a node, and kills the one that's there. It deletes the one that's there. Oh no, delete doesn't get rid of the pointer. Where is temp pointing? Has temp changed at all? Where is it pointing? Where is temp pointing? It's pointing into the address of where there used to be a node. What is in that box now where there used to be a node? What? You don't know. You don't necessarily know what's there. If you were to use this temp pointer and follow it, which is possible, I will tell you, you will end up at a place where there used to be a node. What is there is hard to say. Most of the time, you will find the same values that used to be in that node because it doesn't overwrite them. But sometimes what will happen is between the time you delete it and you go to look at it, something else will have been put in that box, possibly. In which case, there's no telling what will be there. I'm glad we had this discussion because temp is what is known as a dangling pointer. It is pointing off into some place where there used to be something, but now you do not know what is there. This is a bad thing. Okay? This is seriously not just a little bit bad, this is a big bad thing. Like, calling something on temp where it points off and is dangling is very risky. In fact, have you ever heard of a group of people called hackers who break software? If you take more classes and you get to my security class, you will learn that this right here is one of the primary ways or one of the common ways that hackers are able to break into software. Because what will happen is something will get deleted, that space will get reused, and then that new space can still be accessed by that old temp pointer. And so you can start using that temp pointer to mess around in memory that you shouldn't be messing around in. Okay? Oh, and do you remember the day you asked me if we could just randomly do stuff in memory? I figured out how to do that in C++. So if we have time, we can just randomly poke around in memory and see what happens. C++ has a special way of doing it. So. Okay, so, yes, sir. Because programmers are what? Computers are also lazy. So here's what happens. When you delete something, the computer doesn't overwrite what's in that box. It just says, hey, this box is no longer being used. Next time you need something, you can use this one. And so it gets added to the list of places that you can use, of memory boxes you can use, but it doesn't overwrite it. Does that make sense? So, and that's super common in computers. Computers very rarely overwrite stuff, so even sometimes when they should. All right, so what kind of pointer is temp at this point? And dangling pointers are how bad? Very bad. Are they as bad as global variables? They're all bad. Bad is bad, okay? Global variables are also bad. So what do we not use? Exactly. Okay. Global variables are a path to the dark side. They're tempting. You want to use them, but don't. Okay. So here we are. We have this dangling pointer, but we've managed to delete the first node, so we're happy, right? What do we have to do now? Make temp equal what? Temp equal head, because we want to do the same thing on the next part of the list. So we go ahead and move temp there. I think you all see where this is going. What happens now? All right, how many of y'all say delete temp? How many of y'all say move head? Yep, got to not lose our head. So we move the head along. Oh, that didn't work out quite well there. Move our head pointer along. Now what do we do? Delete temp. We just go ahead and delete temp. What is temp right now? Dangling pointer is good or bad? Are they good or are they worse than global variables? They're both bad. All right. So now what do we do? Advanced temp, so it points at head. Now what do we do? Pardon? We just do the same thing, right? We move temp. If we move temp, now we have to do what? All right. So what I'm going to do is, because I'm lazy, I'm just going to advanced head. I'm just like here I said head equals head get next. Head equals, I'm just say head equals head gets next. Boom, head is null. Right? Because I don't want to have to think about whether this is especially the last case or not. But I know when I get to head being null, I'm done, so I will just advance it. Now what do? We delete temp. Are we done? Why aren't we done? We don't care. We're done with temp because it's temporary. But that's fine. Okay, what do you want to do with temp then? Delete temp, but it's got a name. We can't delete things that have a name. We can let it go out of scope. All right, it's okay to have dangling pointers because when I write the code, this is all going to be in a function. Temp will be a local variable and it will go away, okay? It's okay. It's okay to have a dangling pointer as long as you kill it immediately, and that's what we're going to do by making it go out of scope. Okay? We can only kill things that have we can only use delete on things that have an address, not a name. For things that have a name, they have to go out of scope, and then they'll go away. Okay? Does that make you comfortable? It's all right. You all look. All right. So here's our algorithm, right? We get a temp pointer, point it to head, advance head, delete temp, advance temp, right? Advance head, delete temp, until head is null. Got it? Everybody good with this algorithm conceptually? All right, let's go write some code that does this then. So where would we write this code then? If we want to delete the list, where would we write that? Yeah? In the destructor. We can do it two ways. We can either write it directly into the destructor, or we can make another little private method that deletes the list, and then just call that. And that's probably better because sometimes you might actually have, you might want to actually delete the list for other reasons than just being destructed, right? You might build a list and destroy it. So we'll write its own little method to delete this. So this is void, belongs to the linked list class, and it is named delete list. Okay. So what is the first thing we have to do? Do you remember our algorithm? Create a temp variable. And what is that going to be equal to? Head. You do want to initialize your pointers, but you don't have to do it this way. Oops. I mean, you can if you want to, but you might as well just cut out the middleman and just do this, right? It's the same. All right, now what? All right, we're going to have a while loop, and we're going to make sure, because it may be that the linked list is already empty, right? It may be that the linked list is already null, and we don't have to do anything. So we just say while head isn't equal to null. The first thing we do is, so here we are. We've created temp. Now we're going to be in this loop where we move the head, delete, move temp. So what's the first thing we do? We're going to advance the head. How do we do that? Okay, so we advanced head. Now what? Delete temp. And then what? Yep, temp is dangling, so we have to move it someplace. And so we will say temp equals head. And that's pretty much it, because at some point what's going to happen is head is going to advance and be null, and when we come back to this loop, to the top, we will stop. Yep. Because, excellent question. So why isn't it delete star temp? Because delete is programmed to work with pointers, and the parameter it's expecting inside there is literally a pointer. It has a star inside of it, so it's defined that way. So we don't have to dereference it because we know we're working with pointers already. So. All right, let's compile this and make sure it works, and we haven't introduced any gross errors. We have not. Now what we can do is inside our linked list thing, we can just call delete list. Okay. Our destructor can call other methods. So now what's going to happen is we should see when the destructor gets called linked list being destroyed. And as each one of these things gets deleted, we should see each of the individual nodes printing out their message of destruction and terror. Okay? So, shall we run it and see if that's what happens? No? Stop right there. Wait a minute. What went wrong here? Okay, I made an error of some kind. It's not immediately obvious to me what went wrong. So, how about this? We will say, let's put in a little error message. What do we call that? Get data? All right, so we added a little debugging message to see what's going on here. I'm not quite sure why that isn't working. Okay, maybe I didn't run it correctly or something, but now, wait, what happens if we take that output statement out? Okay, good. I don't know why it didn't work the first time. That was strange. Maybe I did I not recompile or something? But now we can see this works as we want, right? We can see we're making the different things. We're putting them on the front of the list, so they're in inverse order. And then when the linked list is destroyed, it goes through and it destroys each thing on the list as it goes along. Okay? So we have cleaned up after ourselves, and we are happy. All right. Everybody understand what the destructor does and what the destructor for a linked list does? Does everybody understand why we need to use a destructor for a linked list? Yes? No? How many of you all understand it? Yep, exactly. So why is because in the class, the linked list class, the only thing we have in there is that pointer to the nodes. When the linked list is destroyed by itself, only the pointer is destroyed, not each of the individual nodes. So if we want to make sure that all the nodes are cleaned up, we have to implement it in the destructor of our own. Okay. Does that make sense to everybody? All right. About the project. You do not have to implement the destructor for the project. You are welcome to if you choose to, but it's not part of your grading because we got to it pretty late. Yep. Yes, but we put this destructor inside the linked list. So we had linked list, and then we created a destructor for the linked list so that when the linked list finished, it would call delete list that deleted each one of the nodes. Right. Yes, sir. Because it's not in the nodes themselves are not in the scope of the linked list class. Nope. Only the pointer to those nodes is in that scope. And the pointer to those nodes does get destroyed. But the nodes themselves will not get destroyed. Things that are called by new, look, here's the deal. I'll make it simple for you, right? Things that go out of scope are things that have names. Do those nodes have names? What do they have? Addresses, yeah. And so that's why. So what goes out of scope is the thing that's holding the address, not the actual node itself. That's why. Yep. So eventually the operating system will delete them when your program ends. But I want you to understand this because as you go on in your computer science career, and many of you seem to be willing to take more computer science, you're going to be writing programs that actually don't end. Okay? Like purposely don't end. If you think about, say, I don't know, what's like the cool thing that you all use today? Snapchat, Instagram? There's something that an old person like me wouldn't have heard of yet? Or does that cover it pretty much? All right, that covers it. All right, which example do you want me to use? LinkedIn, probably. Pinterest, you all look like a Pinterest group to me. MySpace. What? Friendster? Have you ever heard of Friendster? Friendster was like Facebook that came and died when you were all like 2 years old. So, okay. All right, so let's say that we are Snapchat, okay? Snapchat has a computer running somewhere in a computer center that you are talking to, right? Like you send it pictures and it sends you your friends' pictures and stuff. When does that server stop running? When does it stop running? It doesn't. It goes on forever. It just sits there and it says, hey, someone's uploaded a photo. Let me push it out to all their friends. And I'll sit here and wait for the next person to send a photo, right? That's all it does is it will run forever. Now, the problem is that if you are using linked lists for individual users or some of these other data structures that we'll talk briefly about later, if you don't clean up the memory, eventually that computer server memory will be full. And you'll send a picture and the computer will go, well, you sent me this picture, but I have no place to put it. And that's it. Your program will crash. And you can literally run out of memory and crash. Okay. Now, we could write a program that just started running and made lots and lots and lots of nodes, and eventually it would crash. The problem was it would probably take longer than this class because stuff, okay? But if you're running on a big server someplace, your program may never end. And you may be creating and destroying linked lists because you might need more than one, and you need to clean up after yourself. And that's the story of computer science, okay? And the story of destructors. Okay. Everybody good? Any questions about this? All right, now comes the fun part of the semester, where I'm going to teach you something that is actually really fun, that I enjoy. But first, take a minute, stand up, stretch, get your mind ready to be expanded. All right, come on back, because I have a little quiz for you. I have some questions for you that I think be pretty clear things. So, all right, what is this? What is this? It's a linked list. How many elements are on that linked list? Is that a pretty easy question? Okay. How about this one then? What is this? A linked list? How many elements are on that linked list? 2. You sure? All right, you're doing great so far. What is this? A linked list? Is that a linked list? Is this a linked list right there? What? How many all, is this a linked list, yes or no? How many all say yes? How many all say no? Why is that not a linked list? So this was a linked list that had 3. This one's a linked list that has 2. And this one's suddenly not a linked list? Is this a linked list? How many elements are in that list? So is it a linked list? Yes, it is. This is a linked list with 3 elements. You all good with this one, right? You all totally agree that that top one is a linked list with 3 elements. Everybody's good with that. This second one is a linked list with how many elements? 2. This one is a linked list with how many elements? You more comfortable with that now? What? This is a list. It's just a list of one thing. Do you have a shopping list or a to-do list? If there's only one thing on it, does that make it not a list? It's still a list. It's a list with one thing. It's a list with one thing. This is a list with one thing. Do we have agreement on that? Okay, because we really need agreement on this before we go on to the next thing. Yeah. Yeah, a linked list is a pointer to a self-referential object that can point to other objects. And then you can add them all together into a list. That's literally what a linked list is. Boy, man, we're having trouble with this one. I thought this was pretty obvious. What's this one here, the top one? With how many elements? Second one is with how many elements? This one is a linked list with what? Where are we going next? What does a linked list with 0 elements look like? There you go. That is a linked list with 0 things on it. What? It is! This is, by computer science definition, this is literally a linked list. This is a linked list with 0 elements on it. It is. I don't even know. What? It is. It's a pointer. But what is a pointer to? It's a pointer to a node. And a node is what type of object? Self-referential. That's right, because it's 0 items on the list right now. Yeah, absolutely. Here. Let me make a grocery list for you. Great, there's my grocery list. Yay, I got nothing to buy today. Uh-huh. Yeah. Not yet, because there's 0 items on the list. No, it's totally a linked list. It is. It's completely a linked list. Yeah. Okay, that's only a grocery list because I wrote grocery list. This is only a linked list because I wrote node star head. It's literally the same thing. Yeah. No. Oh, no. No. All pointers to an object that can point to itself are a linked list. If head was like an int star or something, can int link to the next one? No, because it's just an int. Yeah. Nope. Because we have 0 stuff there. We have 0 nodes there. And 0 null is what we use to indicate that there's nothing there. Yes. Yeah. right? Just like I have a grocery list over there with 0 items on it. When I say node star head, I have a linked list with 0 items on it. I got to tell you, I've been teaching this for like decades, and this is the first time anybody has ever argued with me about this. Like everybody else is just like, yeah, I see what you're talking about, right? So, what is this right here? How many items are on it? How many items are on this linked list? Everybody on board with that? Because this is important before we go ahead. What? Are you willing to accept it on faith? We can just say by definition, if you have something here that is node star head, right, that it is a linked list. Because it has the capability of adding other things to it that can be linked to. Does that make you happier? All right. So let's go through this one more time. What is this right here? With how many elements? What is this right here? With how many elements? What is this right here? With how many elements? What is this right here? With how many elements? Perfect. All right, now let me show you something that is actually kind of weird. This node right there, right, the node that has 0 in it, what is this right here? Which is what? A linked list with how many elements? Why are you saying, oh no? So look, what we have here is we have a pointer to a node, and the node has some data, but it also has the pointer to another linked list. And in fact, if you look at the way this example is structured, head right here is pointing at this node 10, but node 10 has a pointer to, look, nodes 5 and 0. And didn't we all agree just a minute ago that 5 and 0 by themselves make up a linked list with only 2 items? Yeah? And then if this is a linked list with 2 items, then doesn't node 5 contain a pointer to a linked list with only 1 item? Does it? Right? And then if this is a linked list with 1 item, doesn't it contain a pointer to a linked list with 0 items? Didn't we all agree on that eventually? All right. So a linked list is pretty interesting. It's pretty interesting because you have, to get to the linked list, you have a head pointer, and that points to the head of the linked list. But also, each one of these nodes by themselves contain a pointer to a linked list. Right? I've never felt so hated by you until right now. Like there's so much skepticism in your eyes. You're like, why are you doing this? But isn't this not true? Right? That every time we're adding to the front of the list, we're just adding a node that has a pointer to the rest to another list. Right? Everybody with me? How many of you are with me? How many of you are against me? How many of you are really skeptical about this whole experience? How many of you are questioning why we're doing this? Okay, so here's the deal. Let's say that we were in a situation where we wanted to delete a linked list. And this is the list that we had. It had 0 elements on it. What would we have to do to delete things off of that linked list? Yeah, this one right here. Let's say, here, I'll get rid of all the other ones just to make it clear. So here's our linked list. We have this, and we want to delete all the nodes. We just talked about destructors, right? Say we're writing a destructor for a list, and we wanted to delete all the nodes on that list. What would we have to do? Nothing. Isn't that nice? Don't you like it when you have to do nothing? Wouldn't it? What? Sometimes it might be. Sometimes. In some cases it will be this, though. You agree, right? Yes? All right. All right, so let's bring this other thing back here. Let's say we were working with this list, and we wanted to delete things. What would we have to do? Just delete head? If we wanted to delete this, what would we have to do? Would we have to delete anything else from here? Why not? Why don't we have to delete anything else? I understand what you're saying. There's just one element. How do you know there is just one element? Because you're looking at a picture, right? Can the computer look at a picture? Then how does the computer know that there is only one element on this list? Because this next one is null. Okay? So, we figure out how to explain this. So, here's what we're going to do. We know that in order to delete this linked list, is this a linked list? How many elements are on it? How many do we have to delete if we want to destroy this list? So what do we do to destroy this list? Nothing. Okay. For this list, though, we do have to delete something. What do we have to delete? The node that head points at, right? For this list, what do we have to delete? We have to delete the node that head points at, and then that linked list down there. All right, so I'm going to write a different way of deleting linked lists. Okay? And the way I'm going to write it is through what's called recursion. Anybody ever heard of recursion before? See where this is going then? Okay. So what we're going to do is we're going to write another delete list, and we're going to call this one void. Delete list recursive. And this is another way of doing things. So let's see, we'll go right down here. All right, so it returns void. It's a member of the linked list class, and it is named delete list recursive. And the way we're going to do this is by splitting up our list into sub-lists. Okay? So here's what we're going to do. When we are given the linked list, like this one at the top that has 3 nodes, what we're going to do is first we are going to delete the rest of the list down here, right? Because doesn't this pointer point to another list? So the first thing we're going to do is we're going to delete the rest of the list, and when we are done, we are going to delete the node that head is pointing to. Everybody follow? How many of you sort of got that and how many didn't? You're looking at me blankly. Everybody get it, yes or no? How many would say no? All right, everybody close their eyes so you're not embarrassed. Raise your hands if you don't get it. All right, good, thank you. Okay, so one more time. First thing we're going to do is we're going to delete this list right here. So to delete the whole list with 3 elements, first we're going to delete the list with 2 elements. Everybody see that? Because this list with 2 elements is actually linked in from the head pointer. Everybody see that? Yes, sir. Oh, watch and see, you'll see. But just conceptually, when we want to delete this whole list, the first thing we do is actually delete this smaller list. You with me on that? Okay, we get to the smaller list now. We're going to delete this list, but the first thing we're going to do is we're going to delete the smaller list right here. Now we're going to delete this list, but the first thing we're going to do is delete this list right there. But we already talked about how to delete this list. How do we delete this list? You do nothing, okay? So if we do nothing on that list, can we delete this list? Right? Because we've already deleted that. We know that there's nothing there. So now we can safely delete head, and it will be gone. Now that we've safely deleted head, that means this list is empty, and we can delete this one. Now that we've safely deleted that one, we can delete this one. Okay? So I'm going to show you in code how it works, and we'll go over this again. So here's what we're going to do. We're going to say if, sorry, I messed up. I need a reference in here to say node star. And we're going to say we're going to delete we're going to call this head to delete. So instead of working directly on the private data member, we're going to pass a parameter in to tell which list to delete. Okay. The first thing we're going to say is if head to delete is null, what do we have to do? If we're given a list that has 0 elements, if head delete is equal to null, we have 0 elements, what do we have to do? Nothing. So here's what we do, is we say return. Yep, void can return too, it just doesn't pass a value back. It just says we're done with this function, go back where you came from. Okay? Everybody with me on this so far? Now the question though is, if head delete is not null, then here's what we're going to do. We are going to delete list recursive on head arrow get next node. And what this says is, if I give you something that has a node in it, if I give you something that is a pointer and it's pointing at a node, then what we need to do is delete the list that this points to before we delete head. Yeah. So what's going to happen is, say we pass this first list in, okay? Let's say we pass this first list in, okay? So head points at this node. Is head null? No, it is not. So what we need to do is we need to make sure that any other list that is contained inside this is deleted before we delete head, right? What would happen if we deleted head right now? We would have these nodes. We wouldn't have the dangling pointer. That should have magically deleted too. But we would have these nodes that didn't get deleted, and we would have no way to get to them. Okay? So what we're going to do instead is we are going to call delete on the rest of this, on this list right here, which is a list in its own right? Because didn't we agree that just like this was a list, this was also a list? Right? So we're going to say, okay, before we delete 10, let's delete this list. And so we call on this list. This list looks and goes, oh, head is pointing at something. Before we delete head, we have to delete this list, which is the list that starts with the node 0. So before we delete this, we have to delete this list, but this list is empty, so what do we have to do? Nothing. Okay. So let's go back and look at this again. So here's what we're saying is add element. All right. Here's what we're saying is, if the thing we're supposed to delete is already null, we don't have to do anything. We're done. But if there is something there, then what we have to do is we have to delete that list. Yes? Oh yeah, remember I said get ready to stretch your mind? This is what recursion is. Recursion is calling the same function or method from within that method. And we'll talk more about how this works, okay? Just trust me, take it on faith you can do this right now, okay? Because what happens is the first time it gets called on the original head, the next time it gets called on that next head, okay? So all we do is you say delete list recursive, and then once that is finished, we just say delete head. Okay, so my claim is that this very insane looking thing right here is going to delete the list. And the way it's going to delete the list is that it will start, where'd my picture go? It will start here and it will say, okay, delete this list, but first delete this list right here. And this list actually happens to be this list. right? So before we delete the first one, you need to delete this list right there, which is this list. Before you delete this one, you have to delete this list right there, which is empty, and we don't have to do anything. Yep. Okay, I haven't actually called it yet. Okay, so what I have here is I have head to delete. We haven't actually called it. So what I'm going to do now is I'm going to change the destructor to use the delete list recursive. And I'm going to give it head to start with. And head is the private data member. Okay. Nope, they're not equal, because delete list, when we do delete list, it works right here on the private data member, right? Because this one just works out of the class. This one says start with the list that is pointed to at the private data member head. But remember, head of this list is just one node and then has the head of the next list inside of it. Yep. Exactly. You don't need a while loop. That's what's cool about this and crazy, right? There is no while loop. All right, let me just run this to you and prove it works. And then next class, what we will do is we will get into how it works. Okay? And you will see why it doesn't need a while loop. I'm trying to think of a good analogy, and I'm really disappointed that the cafeteria no longer has those stacks of plates on springs that I talked about before, because I'm saddened by that. Okay, so let's actually make sure this works. What was that called? Oh, seg fault. Who saw that coming? Oh, that's exactly what I have to do. Thank you. Thank you. Thank you. Thank you. I did not notice my own mistake. So I apologize for not understanding it. Yep, that's what happened. Is I was actually using head to delete to avoid overloading head. So, okay, that looks better. All right. Goodbye from node 23, 14, and 9. Anybody notice a difference between that and the other destructor that we used? The order is different, right? This one destroyed last time. If we run, let's see, if we run, what was it, node 6? You can see that it gets destroyed 9, 14, and 23. This one destroys 23, 9, and 14. It does it backwards. Here is what's happening, and I'll have a better picture for this next class, okay? Here is what's happening. We call delete on this list, right? What does it do? Is head null? It's not. So it calls delete on this list right here, right? But this list is exactly the same as the one I have drawn underneath it, correct? Yes? So then what happens is it says, okay, this head is not null, so I'm going to call delete on this list, which happens to be the same as this list down here, right? Now it says, I'm going to call delete on this list, which happens to be this list down here, which is null. So it just returns. Once it returns, it says, okay, delete that. So it deletes the one from the bottom. When that one comes back, it says delete this one. When that one comes back, it says delete this one. Okay. So this is recursion. A recursion is when a method or function calls itself. Okay? We will talk more about this next class. Any questions? I would be happy to answer questions now as well, but we will go into it next class. And this will be the last topic we cover for the semester, because we only have one class left. Can you believe it? Okay, either I have injured your minds or I don't know what's going on. Do you all want to ask me questions? All right, 17-second rules in effect for questions. Go. Yes, sir. I'm going to diagram for you next class. Okay. I could try and do it now, but I realize that we don't have enough time to do it, and I would rather. Do you believe it works? Okay. Everybody believe it works? Does everybody believe it works? Does anybody think that they come up here and diagram how it works? Maybe a couple of you who have done it before, right? In the meantime, I'm going to have to leave that as a preview of coming attractions. But next class, we will start with actually how this works, okay? And I will draw a couple of diagrams to help it. And we will look at one other example of recursion. So, yes, sir?
Is the only reason why you would do this to avoid writing a while loop?
Nope. Other questions? Because it's very powerful. In fact, I've been looking at restructuring this class to teach you recursion before teaching you while loops.